Have you ever gazed at the night sky and wondered why space is black? It's a question that has captured the human imagination since the dawn of time. When we lift our eyes to the heavens, we see a vast canvas, dark and mysterious, punctuated only by the twinkling lights of distant stars. It's easy to think of space as an empty void, a chasm of nothingness stretching out into infinity. But is it really so? In reality, space isn't empty at all. It's teeming with particles, fields, and a host of other phenomena, each playing a part in the grand cosmic tapestry. But why then does it appear so dark? The answer lies in the fascinating interplay between light and the universe itself. To understand why space is black, we need to delve into the nature of light. You see, light doesn't simply travel in a straight line forever. It's absorbed, emitted, and scattered by everything it encounters, from the smallest dust particle to the largest galaxy. When we look at the night sky, we're not seeing the absence of light, but rather its interaction with the universe. Think of the universe as a giant cosmic theater. Each star, each galaxy is like an actor on stage, emitting light in every direction. But not all of this light reaches us. Much of it is absorbed or scattered by other actors, by cosmic dust and gas, by the fabric of the universe itself. And so, what we see is not the full spectacle, but only a fraction of it, the part that manages to reach our tiny corner of the cosmos. And then, of course, there's the matter of the universe's age. The universe is roughly 13.8 billion years old, and light from the farthest reaches hasn't had time to reach us yet. As such, many parts of the universe remain shrouded in darkness from our perspective. The blackness of space isn't a simple absence of light, but rather a fascinating interplay between light and the universe itself. So the next time you gaze at the night sky, remember, you're not staring into an empty void, but into a grand cosmic theater, filled with mystery, wonder, and an endless dance of light and darkness. To understand why space is black, we first need to understand how light and color work. Light, as we know it, is a form of energy that behaves like a wave. This wave-like behavior allows light to travel vast distances across the universe, from the farthest galaxies to our very own living rooms. It's the reason we can see the stars at night, and it's the reason we can see anything at all. But not all light is created equal. Light comes in a variety of wavelengths, and each wavelength corresponds to a different color. This range of colors or wavelengths is what we call the visible light spectrum. It spans from shorter, more energetic wavelengths of blue and violet light to longer, less energetic wavelengths of red light. And right in the middle we have the familiar greens, yellows, and oranges. Now let's talk about how we perceive color. When light hits an object, that object will absorb some wavelengths of light and reflect others. The wavelengths that are reflected are what we see as the object's color. For example, a ripe tomato appears red because it absorbs all colors of light but red, which it reflects back to our eyes. This principle applies to everything we see. The blue sky, the green grass, the yellow sun, all of these colors are a result of objects absorbing and reflecting different wavelengths of light. But here's the thing about space. Space, by definition, is empty. There are no objects in the vast stretches of the cosmos to absorb and reflect light. So if there's nothing to reflect the light, there's nothing for us to see. So we see objects as having color because they reflect certain wavelengths of light. But what happens when there's nothing to reflect the light? We're left with the cosmic canvas painted in the dark hues of the universe. A black space. Space is vast and filled with countless stars. So why doesn't their light color the universe? A question that has intrigued astronomers and stargazers alike for centuries. The answer lies in a fascinating concept known as redshift, a key piece of the cosmic puzzle. Imagine you're witnessing a car race. As a car speeds past you, the sound it makes seems to change. It starts high-pitched as it approaches, then becomes lower as it moves away. This is the Doppler effect, a shift in frequency and wavelength due to relative motion. Now, apply this concept to light. Light, like sound, travels in waves. But unlike the sound of a car, we perceive these waves as colors. When a star is moving away from us in the ever-expanding universe, the light waves it emits get stretched. The colors we associate with shorter wavelengths, like blue and violet, shift towards the longer red end of the spectrum. Hence the term redshift. But here's where it gets even more interesting. The universe isn't just expanding, it's accelerating in its expansion. So the light from those distant speeding stars is stretched not just to red but beyond. It shifts into wavelengths that are invisible to the human eye, like infrared. So when we gaze up at the night sky, we're not seeing the universe as a still picture. We're seeing a dynamic, ever-changing light show. The light from distant stars and galaxies is constantly being stretched and shifted as it journeys across the cosmos. Even though we can't see it with our naked eyes, that light is still there. It's been stretched, it's been shifted, it's been altered by the very fabric of the universe. It's become part of a grand cosmic ballet where light and space dance to the rhythm of time. The light from the stars is there, but it's been stretched and shifted until it's no longer visible to our eyes. That's part of the reason why space appears black. The universe's grand light show is happening all around us. It just takes a bit of understanding to truly see it. But what about the stars closer to us? Why doesn't their light brighten up the night sky? This brings us to a fascinating conundrum known as Olbers' paradox. Named after the German astronomer Heinrich Wilhelm Olbers, this paradox proposes a thought-provoking question. If the universe were infinite, infinitely old and uniformly filled with stars, wouldn't every line of sight end on a star? And if so, why isn't the night sky as bright as the surface of a star? Imagine standing in a dense forest where every direction you look you'd eventually see a tree. Similarly, in an infinitely old and uniformly populated universe, every line of sight should eventually encounter a star. Thus, the entire sky should be as bright as a star's surface. But obviously that's not what we see when we look up at the night sky, so why is that? The answer lies in the concept of the observable universe. The observable universe refers to the portion of the entire universe that we can potentially observe from Earth. The universe might be infinite, but the observable universe is not. It's limited by the speed of light and the age of the universe. Light travels at a blistering speed, but it still takes time to cover cosmic distances. The universe is approximately 13.8 billion years old. Hence, we can only see objects that are within 13.8 billion light-years of us, as their light has had time to reach us. Everything beyond this cosmic horizon is simply too far away. Their light hasn't had time to reach us yet. Because of these limitations, the number of stars we can see is finite. And not every line of sight ends on a star. There are vast cosmic voids where the light of distant stars hasn't reached us yet. And thus the night sky is not ablaze with light, but instead graced with a sprinkling of stars against a dark backdrop. Because of the finite age of the universe and the speed of light, we can only see a small fraction of the universe's stars. This limitation is another reason why space appears black. So, we've learned that space is black because of the properties of light and the universe itself. It's not a mere absence of color, but a distinct feature of our cosmos, linked to the nature of light and the infinity of space. The blackness of space, in fact, is a consequence of the speed of light and the vast distances between celestial bodies. But what does this darkness mean for us? Well, it's quite beautiful when you think about it. The darkness of space is like a vast black canvas that allows the brilliant spectacles of the universe to shine. It's this very darkness that enables us to see the twinkling stars, the swirling galaxies, and the breathtaking nebulae. Imagine for a moment a universe without this darkness. If space were a bright white, we might not see the stars at all. The darkness of space is like a stage for the universe's light show, allowing the celestial bodies to stand out, to be seen, to be marveled at. This darkness also serves a critical role in our understanding of the universe. It's through this inky blackness that we can peer into the distant past, observing galaxies billions of light years away, seeing light that has traversed the vast expanse of space and time to reach us. The darkness of space is quite literally a window into our universe's history. So, the next time you stand under the night sky, gazing up at the stars, think about why space is black. Remember that this darkness isn't a void or an absence, it's a canvas, a stage, a window. It's the backdrop against which the universe paints its spectacular show, the silence that allows the symphony of celestial bodies to play, the lens through which we can observe the distant past. Next time you look up at the night sky, remember, the darkness of space isn't empty. It's a window to the vast, fascinating universe that surrounds us.